Let's explore the generated clocks, focusing specifically on clock dividers. Generated clocks refer to multiple clocks derived from one master clock. These derived clocks are used to synchronize different parts of a system. Why we need to use generated clocks? To answer this question, we need to know that modern system-on-chip designs integrate diverse components, such as high-speed processors and low-speed memory, all within a single chip. These components operate at different speeds, requiring separate clock signals to function efficiently. Since different elements are triggered by different clocks, a single master clock cannot meet all timing requirements. Therefore, using generated clocks helps synchronize different parts of the system, ensuring smooth operation and communication. Note: using multiple clocks without synchronization can cause timing issues. Therefore, deriving generated clocks from a single master clock helps maintain synchronization and ensures smooth communication between different parts of the system. Generated clocks can be derived in multiple ways, including clock dividers, clock multipliers, and clock gating. In this video, we will explore clock dividers. Clock dividers are components that generates a clock of higher period and lower frequency compared to the original source clock. To more understand, let's see how clock dividers work. A clock divider receives an input clock and divides its frequency by a specified division factor, generating a lower frequency output clock. For example, if the input clock has a frequency of 100 MHz and passes through a divide by 2 clock divider, the output clock will have a frequency of 50 MHz. So, how are clock dividers implemented? Clock dividers can be implemented using various techniques and circuit configurations, such as flip-flops, counters, or PLL-based dividers, depending on the required division factor and application. Let's illustrate how clock dividers are implemented using flip-flops. A basic clock divider can be implemented using flip-flops, where each flip-flop divides the frequency of the clock by 2, providing a simple and efficient method for frequency reduction. A D flip-flop can be used as a simple divide by 2 clock divider as shown. Let's explain. As presented in this figure, the inverted output terminal Q par is connected directly back to the data input terminal D, giving the device a feedback as shown. Due to this feedback, the D flip-flop toggles its output every clock cycle, causing the output pulses at Q have a frequency that are exactly 1/2 that of the input clock frequency. Let's illustrate idea of how clock dividers are implemented using counters. Counters can divide clock signals by higher factors, making them suitable for applications requiring precise multi-stage frequency division. A typical example of a clock divider is a 2-bit ripple counter. Let's explain. The D input of the first flip-flop is connected to the inverted output of the same flip-flop. This creates a toggle behavior. The first flip-flop toggles its output every clock cycle of the input clock signal. Therefore, the first flip-flop divides the input clock frequency by 2. The D input of the second flip-flop is also connected to its inverted output, creating a toggle behavior. The second flip-flop toggles its output every clock cycle of the output of the first flip-flop. As a result, the second flip-flop further divides the output of the first flip-flop by 2. Therefore, the output frequency of the second flip-flop is 1/4 of the input clock frequency. We conclude that the 2-bit D flip-flop ripple counter acts as a divide by 4 counter when its output is taken from the second flip-flop. Finally, let's explain why do we need clock division. Clock division is essential when different components in a digital system require lower frequency clocks than the main system clock. It ensures each component operates at its required speed. Additionally, it helps in power saving as lower frequencies reduce switching power consumption. I hope you found this video helpful. Stay tuned for upcoming videos where we'll explore more topics related to IC design.